Hi, everyone. Hello. Hi, everyone. Okay, great. So let's get started. So let's try to recap a little bit about what I've been learning so far. So over the last couple of weeks, so essentially we talk about database systems, and we talk about how to use it essentially as a user. If you think about what database is trying to do, it's actually an intermediate layer between you as a user and your memory system and your hard drive, right? So, and we talk about essentially two different type of interactions. You can ask the database to actually create a table for you, right? So, and then what database is trying to do is going to create the corresponding information on your hard drive. And then you can keep propagate this relation on hard drive by inserting a whole bunch of tuples. Either you can insert that tuple by tuple, or you can just insert maybe a whole file into the database altogether. So another interaction is after you have all those information on your hard drive, you as a user could write a SQL query to query the information. And what the database is going to do for you, given a query, is to bring the information on the hard drive to the memory system and to the database system and return that back to you. And over the last couple of weeks, we talk about different ways that you can actually interact with the database system. And last week, we have two hands-on sessions in which we write SQL queries together to make sure you can know how to query a real-world database systems. And the goal of the database system is to really make sure you as a user do not need to understand how the database is bringing the data from the hard drive to you. So the goal is to make sure you as a user only specify what you want from the database. And the database system will try its best. And sometimes it fails, but the design goal is it's going to try its best to make sure it optimizes the execution of the query to bring the information to you. That's the goal. And we went through a whole bunch of different ways that you can query your data. So here we scope ourselves to those languages that deal with a relational model. And we went through essentially two different categories of query languages. Those that are practical in the sense that you can actually write them in a real-world database systems, and that is SQL. But we also talk about the theoretical foundation, and we talk about different family of query languages. For example, relational algebra and relational calculus, and we talk about the relationships. So we talk about relational calculus is actually more expressive compared with relational algebra. Why? Because all the relational algebra queries will give you essentially a finite answer, giving a finite database, but not all the relational calculus queries will give you a finite answer. So we talk about the different semantic for relational calculus called domain-independent relational calculus, which will always give you a finite answer given a finite database systems. And we show that there's essentially the equivalency between relational algebra and domain-independent relational calculus. And we talk about the two subsets. One is conjunctive query, and another is the relational algebra that with only selection, projection, join, and renaming. And we show that these two small languages are actually equivalent. And then we talk about the practical side. We talk about how to write SQL queries. And there you can see there's a very beautiful correspondence between what you can write in practice and what you can analyze theoretically. We show that if you only have selection, projection, join, and renaming in relational algebra, you can actually specify that in SQL using select from where. Right? And we talk about kind of a larger subset of SQL language that allows you to specify every single relational algebra expressions that you want to write down. And because there's a one-to-one correspondence between relational algebra and domain-independent relational calculus, every single relational calculus queries can be written in this small SQL subset. And of course, we talk a little bit about kind of the larger subset of SQL languages for you to specify things goes beyond relational algebra that we introduced in this course. For example, aggregation, right? Also the subqueries, so on and so forth. And last week, we spent 2 lectures try to walk you through the process of writing SQL queries in a real database systems. So if you want to learn SQL, right? So we are not going to spend too much time talk about kind of the language specification of SQL because it's a language. The best way to do it is for you to actually read all those details. So it's in these 3 chapters in textbook, right? So I mean, if you want to get some hands-on experience, right? So we have 3 code tutorial. You can just follow step by step, right? So and you can look at the hands-on sessions recording, right? So there's exercise session. And another thing that's really important, if you really want to learn SQL really well, is to practice. I mean, I don't know any other way to get around that. Yeah. So starting from this lecture, we are going to switch gear and we are going to go beyond simply writing SQL queries, okay? So essentially, we are going to talk about a different process. So now, given a database system, you as a user, you know how to create tables, you know how to query your data. Starting from this lecture, we are talking about that if you want to build a real-world application, how can you actually design your database schema, and how can you design your query to build such an application? And that is something we are going to talk about. We are going to be focusing on the principles of how to use a database to implement or design a real-world application. So today we are going to talk about the very first step of building a real-world application using a database system, and that is called conceptual modeling. And in the next lecture, we are going to talk about logical modeling, and after Easter, we are going to talk about physical modeling, right? So, but today we are going to talk about the very first step. We will try to understand what it is first, and then we will talk about a very popular way for you to do conceptual modeling, and that is using entity relationship model. Okay, so this is kind of 3 different steps that people always do when building a real-world database system, like when people build real-world applications. So on the left-hand side, you have the real world, right? So you have one application you want to build. On the right-hand side, you have your physical implementation, right? That's a sequence of 0 or 1 representing your data stored on your hard drive. And you as a user, the goal of your exercise is try to bridge these 2 parts, right? So the very first step for people to build a real-world application is called conceptual modeling. Right? So there, the question you really want to understand is how to capture the domain of the application that you want to represent conceptually. Okay? And then you are going to do logical modeling, which is try to convert all those conceptual model into a logical model, right? So and in our case, that is a relational model. Essentially, you conceptually you define what application you want to build, and then you translate that into a concrete relational model, modeling your data. And then a physical modeling is actually how to implement this logical model, this relational model, on a concrete hardware. And for every single step, there's a lot of automatic tools to help you. But you as a user still need to understand how to do each step, essentially how to drive the process of doing every single step. So let's look at a concrete example, right? So this is the example that we have been looking at in our first lecture. Right? So we want to build this bill of material systems to really manage the data that you can see on the right-hand side. Essentially, we want to say, okay, let's build a toy. To build a toy, we need to assemble different parts, right? And we want to manage that. For every single parts, there's a whole bunch of information, like the name of the parts, the quantity of the parts, right? Maybe some pictures, maybe the unit cost, the cost, right? So on and so forth. How can we build such a system? Well, if you want to build such a system, right, as someone who's building it, first, you can actually describe what you want, maybe in English, in natural language, without interacting with the database. For example, here, right? Okay, so the final thing is a product, right? So product has a name, right? So in this thing, maybe it's X-Bin, right? So that's the name of the toy, right? So, and the product, the toy, has a set of parts, right? A part has a name, a part has unit cost, quantity, total cost, so on and so forth. You can describe all you want to do and all the data you want to store, all the query you want to write in natural language. But the problem is that you can never convey that to a machine because the machine will not understand you. To actually build such an application, the very first step is to translate all this natural language specification about your application in a machine readable, precise way. And that step is conceptual modeling. So after this lecture, you are going to learn about essentially one way to do conceptual modeling. And that is by kind of drawing an entity relationship diagram that look like this. So even without talking about all those concepts, right? So like by just looking at this, we kind of have a rough idea about the application you want to build, right? So here you have like one entity called a part, and you have one entity called a product, right? So and you say, there's actually one relationship between part and products, right? So one product has multiple parts, right? So and for each part, you have the name, right? Maybe you have ID, you have quantity, or unit cost, so you have cost, right? Each product has a name, right? So we are going to talk about precisely what this means, right, in this lecture. But conceptually, this gives you a way to convey all the information about this application to a machine. So that is the goal of conceptual modeling. So one thing that you need to be careful about, right, because we are talking about the modeling, right? A model you have actually does not contain things that are common sense, but you didn't tell to the model, right? For example, here, if you give this model to a machine, right, the machine will actually think the cost could be negative, right? But on the other hand, we all know in real world, right, at least for this application, the cost cannot be negative, but that is not in the model, so the machine doesn't know about it, right? So as you can see, the conceptual modeling part already is a kind of a relaxation of the application you want to build, right? So it only contains the information that you put into this model. But nevertheless, it gives the machine some idea about the application you want to build. After you have this conceptual model, right, which is already precise and machine readable, so the second step is logical modeling. And this exercise is really trying to translate your conceptual model, which is the diagram, look like this, into a logical model. And depending on the different database system you are using, there are multiple possible logical models. But in this course, we are going to talk about relational model, in which our data is organized as a set of relations. And every single relation, intuitively, you can think about as something like a table, okay, with some caveats that we talked about a couple of weeks ago. So for example, here, right, so you can take as input this conceptual model for your application and translate that into a relational model. So here I could have one relation store all the part, I could have one relation store all the product, and I could have another relation store the relationship between part and product. And in the next lecture on Friday, we are going to talk about this process. How can you translate a conceptual model into a relational model? And after you have this, you can already write some theoretical queries for this, right? So you can write relational algebra, you can write relational calculus. But to make that really practical, you need to do physical modeling, right? To really try to understand how to implement this into something concrete, right? Specifically, we are going to implement this one into kind of a whole bunch of physical tables stored in real database systems. Right, so this is a physical modeling part, how to translate your logical model in relational model in our course, into a physical representation or representation of your data. So this is the 3 steps that we are going to talk about for building a real-world applications using a database system. Okay, so in this lecture, we are going to talk about the very first step, that is conceptual modeling. And we are going to talk about one way to deal with that, and that is something that we call entity relationship model. Okay, so conceptual modeling. So the goal of conceptual modeling is you can really think about that as building a mini world, right? So we live in a real world with so many details and things we don't really care about in our application. When you're doing conceptual modeling, what you are really trying to do is try to construct a mini world that can just model the application you want, but none of the other details that you don't care about. And after you have this conceptual model, you can then semi-automatically translate it into different logical model. It could be relational model that we are going to talk about in this course, but it could be other type of logical models. Okay. Before we talk about the language we are going to use to do conceptual modeling, let's talk about a little bit about what is modeling, right? So here intuitively, this is how to think about it. So recall that when we talk about a relational model, we talk about the key constraints, right? So for every single relation, there need to be a primary key, right? And that actually specifies all the database instances that are valid or allowed under this constraint. For example, if you have a professor table with 2 attributes, ID and maybe professor name, right? Maybe if ID is the primary key, what you are trying to specify using that is in this application, I'm only allowing a database instance with the following property. That is, if you give me the ID of the professor, I can uniquely identify a professor. I cannot have 2 professors with the same ID in my data. Essentially, when you are trying to do this key constraint, it specifies all the database instances that you are allowing in your application. By conceptual modeling, we are trying to do the same thing. Essentially, we are trying to specify all the database instances that are valid or allowed in my application. And we will see this point really soon, but just keep this in mind. So especially when we are talking about cardinality down the road in this course, you are going to understand this like immediately. But right now, just keep this in mind. At a high level, this is what we are trying to do. Okay. So now let's talk about one way to do this, and that is by something that we call entity relationship model. So essentially, in entity relationship model, we model our application with the following 3 element types. So the first one is called the entity set, which, as the name implies, is a set of similar entities. So what do we mean by entity? So entity here means that an object in real world that is distinguishable from other objects. For example, Professor A, right? So one professor is an entity, another professor is another entity, right? ETH is an entity, right? EPFL is an entity, right? So it's an object in real world. And what do we mean by similar, right? So there are so many different ways we can define what similar means. But here, when we talk about similar, we mean something really precise. We mean entities in the same entity set, they need to share the same attributes. For example, you have 2 professors, 2 professor entities, Professor A, Professor B, right? They all share the same set of attributes. They all have name, they have ID, they have office, so on and so forth. When we talk about 2 entities that are similar in this context, we mean that they have the same set of attributes. So here the example is professor is an entity set, right? And Professor A, Professor B, kind of a specific professor, is an entity in this entity set. And if you are familiar with object-oriented programming, right? So you can think about this roughly in the following way. That is, entity is kind of an object, and entity set is like a class. Okay, so that's roughly how you think about that. If you really want to be precise, the key difference is that when we are talking about entity relationship model, we are talking about a data model. It actually doesn't have method, doesn't have functions. Okay, we only cares about structure of the data. And the second type is attributes. For example, here, whenever I have a name of a professor, when I have an ID of a professor, right? So both ID and name could be attributes. And then we have the relationships between different entities. Relationships are connections among two or more entity sets. So for example, I could have a relationship between professor and lecturer, right? To specify which professor teaches which lecture. I could have relationship between the entity set students and entity set lecturer, right? To specify which student is taking like which lecture. And to build one application, essentially you try to specify what the entity sets you have, what the attributes each entity set has, and also what are the relationships among all those entity sets. So you need a language for you to specify that precisely. And one language we are going to talk about in this course is called entity relationship diagram, which is a graphical way for you to represent entities and relationships among them. So let's talk about a little bit about the basic elements of this language. And then we are going to talk about the formal semantic. So to specify the entity set, you draw essentially a rectangle like this, and you put the name in the middle, okay? And then each entity set, for example, professor, it can be associated with a whole bunch of attributes. And for each attribute, you draw a circle, look like this, and you connect an entity set with the attribute. And of course, each entity set could be associated with multiple attributes, so you do this. So let's look at a concrete example. So assuming you want to say, okay, in this application, I'm going to store a whole bunch of objects with a type person. They're all like people. I could have one entity set called person. And then I say, okay, for every single person that I want to store in my database in this application, all of them has a national ID, okay? And all of them has a passport number, and all of them has a name. So in this case, national ID, passport, and name are attributes, and you connect them with the person entity set. If you want to specify relationships between entity sets, right? So you are going to have multiple of those entity sets, and then you are going to draw something with a shape of diamond, right? And then you put the relationship name in the middle, and you connect it with all the participating entity sets. So here's one example. Assuming in my application, I have a person entity set storing a whole bunch of information of different person, right? Each person has national ID, passport number, and name. I have maybe another entity set with a like lecture. Each lecture has one attribute ID, right? And then I want to say, okay, in this application, I also need to store the information that some person going to teach a lecture. Okay? If you want to do this, you are going to have a teach relationship in the middle, and you connect that with person entity set and a lecture entity set. So this is how to specify this. And you can also have maybe another relationship to say, okay, some person going to takes lecture. Okay? So here you can have another relationship, for example, takes, and you connect that with lecture and person. if you draw a diagram look like this, what you are trying to say is actually to say, okay, I have two entity set, person and lecture, and there are two different relationships between them. A person can either teach a lecture, a person can takes a lecture, right? And that is actually kind of a specification about the data you have in your application. That's what we are trying to do in conceptual modeling. Okay, so similar to a relational model, we also have the notion of key for entity set. So not all the attributes of entity set are equal, right? In the sense that some of them has additional property. So a key, what is a key, right? So key is a minimal set of attributes whose value uniquely identify an entity in the entity set. For example, if I take the national ID attribute, and if I set it as a key, it means that in my application, if you gave me a national ID, it uniquely identifies one person in this entity set. I cannot find another person with the same entity, so with the same national ID. That's the meaning of key. So there are multiple things we need to be careful about. First one, we are talking about kind of set of attributes are key, right? So essentially multiple attributes together could form a key, okay? So that's a type of the key. So there might be multiple keys, right? For example, here, maybe national ID could be a key and the passport number could be a key, right? So all of these are called candidate key. And we can pick one of them and use it as primary key. So I need to actually specify which attribute is a primary key. You just underline it, right? So very similar to what we are doing in relational model. And here, every single entity set must have a primary key, okay? So essentially, this is a valid entity relationship diagram, right? You have person, multiple attributes, and you underline national ID if you choose it as primary key. Okay? So there are multiple things we need to be careful about when we talk about keys. So first one is, let's look at this example, right? So we have person, right? So I want to say, okay, so the combination of nationality and the passport number together is a key. Is that okay? Well, it all depends on your application, right? If you are living in the real world, right? If you look at what the passport number looks like, right? So you can actually find this specification on Wikipedia. You can see that it actually has the issuing country as part of the number, right? So and in this case, the problem could be that passport number already contains nationality information, and therefore the combination of nationality and passport number is not really the minimal set of attributes forming the unique identifier. That is, if I know the passport number, I actually know the nationality, right? Like assuming this is our definition of a passport, okay? So in that case, you cannot use a combination because they are not the minimum set of attributes. Okay. So I see someone raise the hand. Yeah, go ahead.
Yeah, so one question is, what does it mean to have multiple candidate keys if only the primary key can uniquely identify?
Oh, okay, so that's a very good question. Okay, so for every single candidate key, they are able to uniquely identify. For example, here you have national ID, you have passport number. Both of them could uniquely identify a person, right? So essentially you have two candidate keys in this application, but you only pick one as a primary key. So does that answer the question?
Yes, it does. Thanks.
Okay, thank you. Perfect. Okay, cool. So here, the key need to be minimal set, okay? Another thing is, let's think about this, right? So in real world, right, some person can have multiple citizenship, right? So like what can we do here, right? So does this ER diagrams like model this application correctly, right? Well, in this case, I mean, it could have a problem if you set national ID as the key, right? For example, here, if you set national ID as a primary key, right? One person might have multiple national ID associated with them, right? So then this database might have problem in storing all the data, right? For example, it's very hard to put all the national ID of a single person, right, into a database because every single person is associated with one national ID, right? And the national ID attribute is not a list of values, it's a single value, right? So if in your universe that you want to model, that you are allowing like one person take multiple nationalities, right? So then this ER diagram could have a problem, right? So again, right? So model, there's no right model or wrong model, okay? So model is a reflection of all the assumptions you have in your application. So it doesn't necessarily reflect all the aspects of the real world, okay? And it's only reflect the part that you kind of cares about. So for example, if you are building one application in which all persons come from a single country, then this ER diagram is a pretty good model. But on the other hand, if you want to build an application that one person can have multiple nationalities, then this ER diagram is not a good model, right? So again, a model doesn't have the absolute notion of good or bad, right? A model is going to model the real world and lose some precision, right? So the thing that you need to make sure is that it's going to reflect all the aspects that you kind of cares about in this application, okay? So I see someone raise hand. Yeah, go ahead.
Hello. I have a question.
Yeah.
In the relational model, we have keys can have the form of like multiple different, where, for example, like where different attributes form the key, right?
Yeah.
Does the entity relational model not have this function or trait? Because here it's just the national ID or just the passport ID, not multiple attributes build a key together.
Oh yeah, so I mean this is just one application, right? So in an integrational model, like a key is still a set of attributes, right? For example, here if you want to say the combination of nationality and passport number together form the key, you can do this. Right? So you can underline this, you can underline this, and then this will specify the combination of these two is the key.
Okay, so you can do it.
Yeah, you are
can
able
specify as to attributes as the primary key.
Exactly, the combination can be the primary key. Yeah.
Okay, thank you.
Cool. Okay, great. Yeah, so another thing we need to be careful about is not all the candidate keys are good primary key, right? So I think we get this question actually a couple of weeks ago about how to pick the key, right? And we actually like roughly went through this application. Yeah, so this example, right? So there are kind of different considerations you may have in picking the primary key, because when you are picking the primary key in many applications, you are actually saying, okay, so I will actually identify this person using the primary key, right? So as a very, very extreme example, right? So here, actually, no, actually I need to, sorry. So let's look at this example, right? So assume I have a person, I have my national ID, right? So I have maybe magically you can get the current position of a person on Earth, right? So, and yeah, in this case, right? So this is also uniquely identify a person, right? So if I know the coordinate of a person on this universe, like in this universe, right? So I could uniquely identify a person, right? But here, setting this attribute as the primary key might not be the best idea, right? Because it keeps changing, right? So whenever I move, right, I walk around, this value, right, current position on Earth is going to keep changing, right? So even though it could uniquely identify a person in this application, using it as primary key might not be the best idea, right, to do. So here, right, so if you compare which one should you pick as a primary key between current position and national ID, right? So I think a reasonable person would argue maybe national ID is a better choice, right? Okay, so that's all about the keys. So now let's look at a little bit about relationships, right? So each entity site, when they participate in a relationship, can have a role, right? So, and the motivating example is here. So assuming you have a person entity site, and then you want to model the relationship like parent of. One person is a parent of the other person. So in this case, right, so you are going to have a relationship parent of here. And then you are going to connect it with person, right? And also connect it again with person, right? Because both participants of this relationship are coming from the person entity side, right? But the problem here is that I kind of need to distinguish these two lines, right? I need to tell the system, okay, one of this is a child, another of this is a parent, right? So in this case, you can actually write the role here, which says that, okay, so this participation is a child, this thing is a parent, right? So you can just write the name there, right? And we call this name the role of this entity set in this relationship. Okay, so now let's look at one concrete example. So let's try to model kind of the university, right? So that we have been looking at over the last couple of weeks. So let's represent it in entity side attribute relationship and the key and the role, like apply all of this. So this is one potential ER diagram of this application. So let's read it together, right? What does this diagram tell us about the application that you want to build? So if you read this diagram, right? Okay, so I have 4 entity sites, right? So in my application, I have essentially 4 kind of collection of entities. You can think about it in that way. I have a whole bunch of students. This is student entity site. I have a whole bunch of lectures, I have a whole bunch of professors, I have a whole bunch of assistants. Okay, and every single entity site, right, contains a whole bunch of entities. And for every single student, I have 3 attributes, right? And for every single lecture, I have 3 attributes. For professor, 4 attributes. For assistant, I have 4 attributes. For professor, you can think about, okay, I have personnel number, I have a name, I have a room, I have a level. And here I pick personnel number as a primary key, which means that if you give me the personnel number of professor, I can uniquely identify a professor in this professor entity set. And then I have a whole bunch of relationships between these entity sets. For example, if you take this relationship, attends, right? It connects students and lecture. It means that, okay, students attends lecture. If you think about requires relationship, it actually connects lecture and lecture, right? It means that one lecture, the role is prerequisite, another lecture, the role is follow-up, okay? And then you can have this 3-way relationship. For example, you can say, I have a test relationship connecting students, lecturer, and professor, right? So essentially, it says that, okay, student take this lecture provided by this professor, okay? So that's a relationship between 3 different entities. And then sometimes you can actually have attributes for relations, right? So here you say, okay, essentially for every single relationship between student, lecturer, and professor, there's also an attribute, which is grade, right? Very similar to the notion of attribute for entity set. Here you can also have attribute for relationships. And you can actually do this exercise of reading this diagram by yourself. So as you can see, it's really giving you a very precise specification about what you want to build. So one thing that could be interesting is that there are a lot of entity relationship diagrams look very similar, right? But they actually mean different things. So when you are reading an entity relationship diagram, you really need to be careful, So let's look at these two examples, the one on the left-hand side and the one on the right-hand side. So what's the difference? In both examples, I have three entity sets: student, lecturer, professor. So in the first example, on the left-hand side, I have a test relationship, which is a three-way relationship connecting student, lecturer, and professor, right? Student take the test of this lecture provided by this professor, right? And I also have another relationship connecting professor and lecturer. This professor gives this lecture. On the other hand, you have a test relationship connecting student and lecturer, right? So you have another gives relationship connecting lecturer and professor, right? So difference is pretty clear, right? So in the right-hand side, whenever students are taking a test, they actually do not know essentially which professor provide that exam, right? So that's the only difference. On the left-hand side, whenever students take a test, you actually have another piece of information that is which professor provided the exam. So which one is better? Well, that actually depends on the application on the universe essentially you want to model, right? Like hypothetically, if you live in a universe where the professor gives a lecture, is always a professor providing the exam, right? And then maybe the one on the right-hand side is a better example. Because if you have that property in your application, the one on the left-hand side is going to store kind of redundant information, right? But if you live in a universe where you have two professors, one professor gave the lecture of database, another professor provide exam for the database course, then the one on the left-hand side is a better example because the one on the right-hand side is going to lose information. So which one is better is actually depends on the real world application that you want to build. Okay. Yeah, go ahead. There's one question.
Yeah, I wanted to ask, so you said the left one would be better if we have one professor giving the lecture and another professor doing the tests, but I would actually disagree, or at least what about so one lecture is held by different professors. This is even normal at ETH, right? So wouldn't the left, so the left one be better as well? Because some students maybe write, I don't know, algorithms and data structures with Professor A, and then 3 years later, students from three years later write the same subject, but by a different professor.
Oh, exactly. In that example, yes. Yeah. So in that example, I think the one on the left-hand side is actually, well, I mean, if that is application, I would model that in a different way, to be honest.
Okay.
Yeah, so if that's example, yeah, so I would actually model that in a different way. But assuming I can only pick between these two, then in your application where multiple professors can teach one lecture and student can actually take tests provided by different lectures, like provided by different professors, then I think the one on the left-hand side is better. Yeah.
Okay.
Yeah. So when I talk about that, like my mentality model is one lecture is taught by one professor. Yeah. Okay, cool. Yeah, so like which one is better actually depends on the application you want to model. Okay. So another thing about entity relationship diagram is that people often make mistake is about, because it's so close to the real world, people sometimes put in some common sense into the diagram, in the sense that they try to read from this diagram something it actually didn't model. Okay, so that is actually very important. It doesn't matter how close this diagram is to real world. Your common sense in real world is not in this model if you do not specify it. Okay, so for example, here by reading this, there are a lot of information that we cannot get from this. For example, we will not know whether students are friends with each other. We will not know which lectures that each assistant is helped with. Right? We don't know how many lectures each professor can teach. We don't know, like essentially, like how many professors can teach one lecture, right? So all of this are not in this model, right? So all you can read from this model is what's specified in this model. That might sound like a trivial statement, but you'll be surprised how often people actually try to read information from a model that's actually not there. Okay, so that's very important. All we have is a model. It's a reflection of a whole bunch of assumptions we have on this universe. Okay, whatever is not in the model is not in the model. You cannot read that out. Okay, so essentially the diagram does not contain information that it does not model. It sounds very like a trivial statement, but you will be surprised how often people make the mistake. Okay, so let's take a break. When we get back, we are going to keep talking about ER diagram, and we are going to make that more precise by introducing the formal semantic. Yeah. If you have any question, just speak up. Yeah.
Hi, I have a question.
Yeah, go ahead.
In the relation, the suggests the relation, for example, does
Yeah.
it matter where the arrows or where the lines enter? Or from the top or from the bottom or from the sides? I don't think it does, but I wanted to make sure.
Oh, that's a good question. It doesn't. Yeah.
Okay, thanks.
Yeah, so sometimes it look very confusing. For example, I could have like this line enter here, then look very weird, right? But it doesn't really matter. Yeah, so just when you read it, you need to be careful. Yeah, so it doesn't matter.
I would have a question. Are you here, Professor?
Oh, sure. Yeah, go ahead.
Okay, thank you. I'm trying to think of a way to intuitively understand the relationships. And what I came up with is that the relationship would map an instance, for example, of professor to a subset of courses and a subset of textbooks. Would this be a correct characterization of relationships?
Okay, so that's a very good question. So we will talk about that in the second half of the lecture. So essentially, whenever you have a relationship, you are actually, in principle, generating a logical sentence. Okay, so like we are going to define relationship in a very precise way. Yeah, so in like 20 minutes. Yeah, so like if after that part you still don't know the answer of your question, ask again. Okay, yeah.
Okay, thank you.
Like yeah. So like that's a very good question. Yeah. So because if you just look at all we have been talking about, the notion of relationship might sound really vague, right? What do we really mean by that, right? So we will try to make that very precise. Yeah.
Okay, yeah, because for example, this multi-way relationship isn't really clear to me at all. I mean, you said down there assume, but without the assume, I wouldn't really understand what it means. So the semantics aren't really clear without the assumptions.
Yeah. So like here, like right now, you can think about this relationship suggest as a collection, as a set of three tuples. As a set of tuples, each tuple has three values: a professor, a course, a textbook.
Okay, and the relationship would then be a relation on the set of these three tuples.
Exactly.
Or would it be just a set of these three tuples?
Sorry, can you say it again? Yeah, sorry. Yeah, sorry, I didn't hear you. Yeah, sorry.
Okay, I think you will cover this, so I don't want to spend too much time on it. But the only question was if then the relationship, would it be a mathematical relation on the set of three tuples, or would it just be the set of these three tuples that you mentioned?
It's a mathematical relation over these three sets.
Okay, thank you. This answers my question, I think. Thank you.
So, and then it's a subset of the cross product between these three sets, right? It can be represented in that way.
Okay, yes, thank you, exactly. Thank you.
Yeah. Sure.
Hello.
Hello.
I have a question. It's not about this part now, but so 2 weeks ago we were talking about the contents of like the chapter 6 of the Stanford book, right?
Yeah.
And we never talked about transactions in SQL, right?
Oh, that's true. The transaction part is going to be toward the end of the course.
Okay.
Yeah.
So I was just wondering because like I think I remember asking 2 weeks ago, it's like do we have to know the entire chapter 6 already? Because you never talked about this, so I was just wondering. I want to ask. Thank you.
So after the whole course, you will know the whole chapter 6. Yeah, but so far we haven't talked about transaction yet.
Okay, thank you.
Yeah, sure. Okay, great. So let's get started. Yeah. So here, right? So one really good question during the break is, what is relationship, right? So here you can think about one relationship as essentially a finite mathematical relation between all the entity sites, right? So here the kind of suggest relationship, right? So one instance of that is a finite subset. It needs to be finite. So I mean that's like really important. It needs to be a finite subset because your database is finite. Okay, it's a finite subset of the cross product between professor, course, and textbook. Okay. Okay, great. So if you have multi-way relationship between different entity sets, that could get tricky, right? So let's compare these two examples, right? So on the left-hand side, you have a three-way relationship between professor, course, and textbook, right? On the right-hand side, you have essentially two binary relationships. You have suggest between professor and textbook. You have use in between course and textbook. So what's the difference between these two? So if you look at this, right? So on the left-hand side, this actually means that whenever a professor teach a course, he or she will always suggest a textbook, right? So essentially, whenever this relationship is always a three tuple, it's always a tuple with three values. There's a professor, there's a course, there's textbook. Okay, so this is what we mean by the diagram on the left-hand side. But on the right-hand side, right? So you can say, professor suggests a textbook for a course, like professor suggests a textbook, and the textbook is used in a course, right? So, but in this case, you could have an example where, like professor suggests, for example, multiple textbooks, and only one of them is used in a course, right? You could have a textbook that participate in the suggest relationship, but does not participate in the used in relationship, right? So I mean, that's the difference, like between these two examples. So now let's look at this example, right? So what if I have kind of a teacher's relationship between professor and the course, right? So I mean, in this case, I mean, still not equivalent to the diagram on the left-hand side, right? So for obvious reason, right? So here I only have essentially two binary relationships, right? So I cannot like essentially fully recover like a three-way relationship. And similarly, right, when you go home, you can actually look at this, right? So it's very easy to give a counterexample showing that these two are not really equivalent. So, but what about this, right? So what's about this? So I have a three relationship on the left-hand side, and I have three binary relationship on the right-hand side. Are they equivalent, right? So in this case, right, so I have professor suggest textbook, I have textbook used in a course, I have professor teaches course, right? So like in this case, it's still not equivalent, right? For example, you could have cases, for example, I as a professor suggest a textbook for machine learning course, so I suggest a machine learning book, and the database book is used in a database course. I teach database course, right? So and this will never happen on the left hand side, right? So as you can see, combining like three different binary relationship, that's not equivalent to a three-way relationship. So, but what about this? This gets a little bit more interesting, right? So I really want to kind of represent my three-way relationship using binary relationships for whatever reason, actually for some good reason. So what can I do? Are these two equivalent? So on the left-hand side, I have my three-way relationship. On the right-hand side, I introduce and kind of one additional entity set called recommendation. Okay. And then I have 3 binary relationships between professor and recommendation, recommendation and course, recommendation and textbook. Which essentially means that, okay, if you give me one recommendation entity, it has professor, has course, has textbook. Are these 2 equivalent? So this is actually very interesting. First one is whatever you can model on the left-hand side, you can actually represent that using the model on the right-hand side, right? So essentially for every single 3 tuple in the database, I could give them ID and make them one recommendation entity, right? And then I can actually represent whatever database you can represent on the left-hand side using the model on the right-hand side. So that's good thing. However, as you will see, these 2 are still different in the sense that the model on the right-hand side is actually models kind of a larger set of database instances. There are database instances that can be modeled by the right-hand side, but not by the left-hand side. So for example, in the model on the right-hand side, you could have kind of professor make a recommendation. This recommendation is also associated with a course, but there's no textbook, right? So because there's no constraints on this model, that one recommendation should participate in all of these 3 relationships. But on the other hand, if you look at the model on the left-hand side, you always have professor, course, and textbook kind of together. Okay. Okay. So this is entity relationship diagram, right? So as you can see, it's a graphical way for you to model your data. So people often think about that in the graphical way, right? Like drawing a whole bunch of things. But this does not mean that ER diagram is vague or imprecise, right? So actually, there is actually a very, very formal semantic behind the entity relationship diagram. And that's something we are going to talk about right now. So if you think about how to define the formal semantic of ER diagram, it's actually pretty natural, right? It's a modeling language. What do we mean by that? It defines the set of database instances that it allows. So essentially, all we need to do is, given an ER diagram, we need to define formally the set of database instances that it allows. Okay, so that is the exercise we are going to do. If you are able to do that, we then give the ER diagram kind of very precise semantic about what does it really mean when you draw a relationship on a piece of paper. Okay, the formal semantics. So ER diagram is a constraint language. It defines a set of validated instances. So assuming that we have all the value we can take in a databases with 2 parts, B and delta, right? B is all the concrete values, like integer, string, floating point, something like that. All of those values belong to set B. And we have a whole bunch of abstract values. They actually are those values corresponding to an entity. For example, Professor A is an entity, Professor B is an entity, right? So all of this are in the set delta. All the value we can take in the database belongs to one of these 2 sets. Whenever you have an entity set in your ER diagram, what you are trying to do is actually introduce a predicate with only one parameter, right? For example, you have entity set E, right? So what you are actually trying to do formally is actually have one predicate EX. And semantically is this predicate is true if and only if X is of entity type E. Okay, you have one abstract value, right? If X is belongs to this entity set, then EX will be true. If X is not of the entity set, then EX is going to be false. Okay, whenever you draw kind of one rectangle on a piece of paper, down like underneath the cover, what you are really trying to do is really try to specify one predicate EX. Okay? And similar attribute, whenever you have an attribute A, what you are actually trying to do is you have a binary predicate AXY, right? Where X takes a value like take an abstract value belong to an entity, and Y takes a concrete value. And AXY is true if and only if the entity X has attribute Y. Okay. And then whenever you have a relationship R with N participants, essentially what you are trying to do is try to generate a predicate R, X1 to Xn, right? And the Rx1 to Xn is true if and only if the entity X1 to Xn participate in R. Otherwise, Rx1 to Xn is going to be false. And then because now we talk about first order logic, right? A first order interpretation of this is essentially interpretation for the entity side, right? Belongs to the abstract value, right? So the interpretation for kind of the predicate correspond to attribute, right? So it's a cross product between the abstract value and the concrete value, and the interpretation for the relation, right? So essentially, it's a cross product like between like the abstract values. So each of the subgraph you have is actually introduce a first order logic sentence. This can become very concrete. So assuming I have a diagram look like this, I have two entity sites, E1 and E2, and I have one relationship linking E1 and E2. Whenever you draw this in your ER diagram, essentially what you are trying to say is a very precise first order logic sentence look like this. Essentially, you are saying that in my database, what are the database instance I'm allowing in this application? In my database, if you give me one entity X1, another entity X2, if X1, X2 participate in R, meaning that if R, X1, X2 is true, it implies that X1 must come from entity set 1, and X2 must come from entity set 2. Okay, so essentially, whenever I draw this, I'm actually underneath the cover specify a very precise sentence look like this. And whenever you give me a database instance, I can actually check very precisely using this sentence. If this sentence is valid true, it actually means that the database instance you are giving me is actually consistent with this model. Otherwise, the database instance that you are giving me is something I'm not allowed under this conceptual model. Okay, so formally, this is what we are trying to do when we are doing conceptual modeling. So here, right, so they tell us, right, Y database instance should satisfy that if X1, X2 participate in R, right, it implies that X1 belongs to E1, X2 belongs to E2. And essentially, relationship is simply introducing a type constraint. Okay. So, and if you have this, have entity side and attribute, so essentially what we are trying to do is actually try to have like the essential sentence look like this. For every single entity, if this entity belongs to entity set E, if this one equal to true, it implies that, so here we have syntax sugar, this actually means there uniquely exists a Y such that AXY is true and Y is a concrete value. Okay, so whenever you have entity side and attribute and you connect them underneath the cover, you are actually telling the database this very precise sentence. So essentially, the attribute specify unique association between abstract value, which is the entity, and the concrete value. whenever you have an ER diagram that look like this, right? So it's actually generate kind of a collection of sentences. For example, if I take, for example, the entity side professor, if I look at this attribute, right? This subgraph is going to generate a sentence look like this. For every single professor attribute, right? Like for every single entity, if it's a professor, it implies that there's a unique concrete value n, which is associated with this professor. Okay, so that's precisely what we are trying to say. And if I look at this three-way relationship suggest, right? So what is it trying to tell us? Essentially saying that, okay, if you give me three entities, P, C, and T, right? If these three things participate in suggest, it implies that P is a professor, C is a course, T is a textbook. Okay. So, I mean, you might wonder why do we really go through this exercise, but this one will become really, really important when we talk about cardinality, when we talk about cardinality. Okay. So right now it might sound a little bit trivial, right? But down the road, you will see why this one is useful. Okay. So now, right? So the tricky thing that we talk about, multi-way relationship, right? So you always see the question like, whether two diagrams are equivalent or not, right? So yeah, of course, like for most of these things, you can actually read this diagram. You can find counterexamples. But if you really want to do this formally, right? So when people are asking whether two diagrams are kind of equivalent, what they are actually trying to say is, okay, so for every single ER diagram, I have the collection of first order logic sentences. Are they equivalent? This is actually what people are really asking fundamentally when they're asking whether two ER diagrams are equivalent or not. In the exam, you might not need to do this, right? Because most of the examples are kind of easy. But if you have a huge ER diagram that cannot be checkable by human, right? And you want to say, like, are these two equivalent? Are the two huge ER diagrams equivalent? There exists kind of a very systematic fundamental way for you to do it. So this is the formal semantic. I mean, it sounds very simple, but remember that it's going to become very, very, very important when we talk about cardinality. Okay, so now let's talk about another concept in ER diagram. So assuming we have professor and we have course, and we have one relationship between professor and course, saying professor teach courses. We know how to represent it right now. But what if I want to introduce additional constraints? For example, what if I know in my application, one professor only teaches one course per semester? Okay, in this case, we need something additional to specify this knowledge. Because if you just take the relationship, connect that with professor and course, you actually do not have this piece of information in your application. But what if I really want to introduce this constraint? So this gives us something we call cardinality of a relationship. So there's something called one-to-many relationship, okay, which kind of like defines the following constraint. If we say there is a one-to-many relationship between entity side A and B, what we are trying to say is something look like this diagram. That is, I have multiple entity side. So I have multiple entities in A. I have multiple entities in B. Right? One entity in A can be associated with multiple entities in B, but I cannot have two entities in A linked to the same entity in B. Okay, I cannot have this link. If I say there's a one-to-many relationship between A and B, essentially I'm saying that in my database, I can never have this link because there are two red entities linking to the same blue entity. Okay, so like precisely, right? So if A is in a one-to-many relationship with B, it means that if you have one entity from A, it can have multiple relationship with B, and one entity from B can only have relationship with one entity from A. Okay, so when you have this type of relationship, you can actually use this notation in your ER diagram. You can write n here and specify many, and you can have one here, specify essentially one. Okay, so this means that there's a one-to-many relationship between A and B. Okay, so the way to read it is actually if I know the entity on the n part, on the many part, if I know this, I can uniquely identify A. Okay, so I cannot have two different A connecting to the same B. Okay? And in this example, you want to say, okay, one professor only teaches one course per semester, right? What you are going to do is, okay, so there's a one-to-many relationship between course and professor. So the course is the one part and professor is the many part. Okay, if I know a professor, I can identify the course. Okay, one professor can only teach one course per semester. Similarly, there is the many-to-one relationship. It's actually the other way around. So what if I want to introduce a constraint that one course can only be taught by one professor? Yeah. In this case, there's the many-to-one relationship. The illustration looks like this, right? So if A is in a many-to-one relationship with B, it actually means that I do not allow this link. Okay, I essentially cannot have one entity A be connected to multiple entities in B. So similarly, if you want to draw it on the ER diagram, you have something like this. A and B, A participate in a many-to-one relationship with B. You have the N here to specify A is the many part, B is the one part, right? So, and this means that if I know the value of A, I can uniquely identify the value of B. And in this case, if you have N here, you have one here, right? So essentially you say, so course participate in a many-to-one relationship with professor. This means that if you give me a course, I can uniquely identify a professor. Okay, makes sense? So, and then there are other type of relationships, right? So what if I want to say one course can only be taught by one professor and one professor can only teach one course, right? So here's the one-to-one relationship. So we say entity set A is one-to-one relationship with entity set B if the following is true, right? Essentially, one entity from A can only have relationship with one entity from B, and one entity from B can only have relationship with one entity from A. So intuitively, it looks like this, right? If there's a one-to-one relationship between A and B, essentially I'm saying I do not allow this link. So like one A can only link to one B, right? One A link to one B, and cannot have this type of cross link, like between A and B. Okay. If you want to specify that in an ER diagram, right? So you just write 1, 1 here, saying that A and B participate in this kind of one-to-one relationship, which means that essentially if I know B, I can specify A. If I know A, I can specify B. Right? If you want to say one course can only be taught by one professor and one professor can only teach one course, right? In your ER diagram, you write something like this. You have one here in the professor side and one in the course side. For completeness, there's a many-to-many relationship, which pretty much means you can do whatever you want, right? One A can be connected to multiple B, one B can be connected to multiple A, right? So this is the many-to-many relationship. This is the default setting if you do nothing, right? So and you can either just do not write A and N, right? But if you want, you can write N here, you can write N here, right? So and in this case, if you see a ER diagram look like this, right, it actually means that, okay, one professor can teach multiple courses, one course can be taught by multiple professors, right, in this application. So formally, what does this mean, right? So here's a formal semantic, and you can see like the reason we really want to introduce a formal semantic in the first place, because that makes the cardinality really, really kind of precise and clean. So in an ER diagram, for example, you have a multivariate relationship R. It's become a little bit tricky to specify one to many, many to one, because there are different participants. Right? But in the ER diagram, you can still write the one here, n here, n here, one here, right? So when you see an ER diagram look like this, what does it really mean? So here's what it means. Essentially, for every single one in the ER diagram, it introduces one constraint. Okay, so in this ER diagram, it's going to introduce two constraints, because there's a one here, there's another one here. Okay, for every single of one, you introduce one constraint, and that one constraint looks like the following. So if you look at this thing, like this one, what it's trying to say is that if you gave me the value of B, C, and D together, you can uniquely identify a single A. Okay, it means that in this relationship, I cannot have two different configurations. Sorry, yeah. So sorry. So I cannot have the same value of B, C, and D, the combination, associated with different value of A. Okay, precisely it means this. If you give me four entities, XA, XB, XC, XD, if XA, XB, XC, and D participate in this relation R, it implies that you cannot find another XA prime that also participate in this relationship, and XA prime that's not equals to XA. Okay? It means that if you give me B, C, and D, I know A. Okay, so this is what this one really means. And then the second one here, the one on the C side, is specify a first order logic sentence look very similar. It means that if you give me A, B, and D, I can uniquely identify C. Okay, precisely this is what it is. You give me four entities. If these four entities participate in this relation R, it implies that I cannot have XC prime that also participate in this relationship, and XC prime doesn't equal to XC. Precisely when you are writing this cardinality thing in your ER diagram, this is what you are trying to say. Okay. Essentially, a validated instance need to satisfy the above two sentences. Okay. So intuitively, again, right? So if you have ER diagram look like this, it means that if I know A, B, D, I know the value of C. If I know B, C, D, I know the value of A. Okay. Okay. So now let's look at some example. Cardinality is it's kind of tricky. Okay, so you need to be careful. Whenever you are not sure, go back to the formal semantic. Okay, that can always give you a very precise guideline about what is allowed and what is not allowed. Okay, but in most of the cases, you don't have to. Okay? So let's look at this example. I have student, professor, topic, and I have relation R connecting them. So, and I have my cardinality, the student is N, professor is 1, topic is 1. What does this mean? It means that in this relationship, if I know the value of student and professor, I know the value of topic. If I know the value of student and topic, I know the value of professor. Okay. So let's look at some example. Yeah, go ahead. So I think there are questions.
Yeah. So would it be enough if I only know the value of professor that I know the value of topic?
No. Yeah. So that's not the the semantic. Yeah.
But why not? I mean, it's one-on-one, right? So if A is...
because so because three-way relationship, it's not really clear what do you mean by one-on-one, right? So here, so that's a tricky part. So when we have one and one here, it doesn't mean any subset participate in a one-to-one relationship. So like this syntax means a very, very precise thing. So you cannot take a subset, because whenever we have this is a definition. So like this is what we are trying to specify.
Okay.
Right. So like if you want to specify like what I'm talking about, you need to invent a new semantic, a new syntax. Right. So here, whenever you see this, like because it's a precise language, right? Whenever you see this, you mean these two sentences. You cannot take a subset. Yeah. So the semantic doesn't allow you to do that.
But does that mean if I have, so like in this relation, no matter what, if it says 1 or n, that I can uniquely identify, so C is 1, so that means I can uniquely identify A, we have A, B, and D, I can uniquely identify C, right?
Yeah.
And the converse is true for it's also true for A. Can we say something about B? No, right?
No. So there's nothing you can say about B. Yeah.
Okay, thanks.
Yeah, so like this syntax corresponding to this semantic, which says nothing about B. Yeah. Make sense? So if you want to say something about B, you need to have a different graph.
Okay.
Okay.
That makes sense. Thanks.
Okay, cool. Yeah, so so this one gets really tricky, but go back to the formal semantic. Okay, so here it looks like a diagram, but it could look very vague, right? But underneath the cover, right? This picture, this diagram, is just some intuitive way for you to specify those logical formulas. Okay, it doesn't have anything go beyond that. You cannot take the subset of the graph, right? So it doesn't specify that. Okay, cool. So I think we have another question. Go ahead.
It was about the slide before again. It's just could we make an even like at the statement at the bottom? Could we make an even stronger statement by saying if we knew A, we can uniquely identify C, and vice versa?
No.
Right.
No. Right. So here you need to know the combination of A, B, D, then you know C. For example, you could have in the database A, B, D, A, B prime, D prime connecting to the same C. That's fine.
Okay.
Right? So like
it's fine.
So like look at these two sentences, right? These two sentences does not imply what you want to say.
Okay.
Right?
I think I get it.
Yeah. So it's very tricky, right? So that's why we have the formal thing, right? So you cannot take the subset of graph to say, okay, if I look at A and C, that seems to be a one-to-one relationship. No, it doesn't work that way. Yeah. So you need to take the whole, because we never define the semantic of a subgraph here. Okay. You take the whole. You have two sentences. Whatever you can prove given this tool is fine. Whatever you cannot prove is something that we didn't specify in the model. Right. So if you take the two sentences, you cannot prove that A can imply C, right? Like A can identify C, right?
Okay.
You can have counterexample for that. Right? Okay, makes sense?
Yes, it does. I realized where I went wrong.
Yeah. So that's very tricky, right? So that's why we have the formal thing, because like in 2016 when we teach the course, if you do not have the formal thing, we get into a little bit of philosophical discussion about what the connectivity really is. But precisely, this is what it is, and nothing else. Okay, it's very, very precise. Okay, so let's look at some example. Whenever you are not sure, go back to the formal semantic. Okay, so if I have an ER diagram look like this, it means that if I know the combination of student and professor, I know the topic. If I know the combination of student and topic, I know the professor. Nothing else. And this graph tells you two things, nothing else. So is this database valid under this model? You have student 1, you have professor 1, topic 1. You have student 1, professor 1, topic 2. To check whether the database instance is valid, right? You just check that 2 sentences. Given a student and professor, do I uniquely identify topic? So here is not the case. I have student 1, professor 1, student 1, professor 1, they're the same, but they link to different topic, right? So which means that this database instance is not allowed under this model. Yeah, so we have one more question. Go ahead.
Could we say that student and professor, it's not completely correct, but student and professor is basically a key for topic? I mean, it's not attributes. Yeah, but I mean,
yeah. So that's a very good question. Yeah, so that's a very good question. So in the next lecture, you are going to see if you represent R as a relation in a relational model, student and the professor is the key of that relation. Make sense? So if I store R as a table, as a relation in the relational model, okay, then student and professor is a key. Yeah, right.
Exactly. That was what I meant.
Yeah. But in ER diagram, there's no key of relationship, right? So that's a little bit tricky, right? So in the ER diagram, student and professor are not the key for R, but when you represent this R as a relation in a relational model like a table, student and professor is a key or is a candidate key of that relation. And similarly, student topic is another candidate key of that relation. Which are the primary key? We are going to talk about it later, right? But they are all candidate keys. Make sense?
Yeah, thanks.
Perfect. Okay, so now let's look at another example. Okay, so if you have a question, just ask, right? So this part is really tricky. It's really tricky. Okay. So is this database, second one, valid under this model, right? So in this case, you check the 2 sentences. Student, professor, identify topic, is that true? Yeah, in this case, it's true, right? So I have 2 different combination of student and professor, they link to different topic, right? So I don't care about that, right? So that's okay. So second one is student topic, identify professor. You can see here, okay, I have student 1, topic 1, student 1, topic 1, they're all the same, but they link to different professor, so this is not valid, okay? What about this one? Again, the same thing. You have 2 sentences specified by this model, you check them and nothing else, okay? So in this case, student, professor, identify topic, student, professor, topic, fine. Student, topic, identify professor, student 1, topic 1, student 1, topic 2, there are different combinations. They can do whatever they want, essentially. This one's fine, okay? What about this one? Again, the same thing. That's student and professor, identify topic. Yes. That's student topic, identify professor. Yes, fine. Okay. So this is cardinality. Whenever I have this n and 1 kind of notation, I kind of essentially generate a whole bunch of constraints about which subset of attribute identify which attribute. If I want to check which database instance is allowed, I just check that logical sentences and nothing else. Okay. So I think we have one more question. Yeah, go ahead.
Yeah, so this may be obvious, but I'm not sure. So could we also say that if we check every subset, right? So if we check the subset topic professor and the subset topic student, that if that holds for all subsets, then we have a valid instance. Maybe that's equivalent to what you're saying, but we're saying, so for example, in the second example, we have student to professors, or like we have student 1 to professor 1, which, okay, and student 1 to professor 2, which would basically not fulfill the subset of, so if we take the subset of the relation only containing topic and professor, then that would not be correct.
I'm not sure I understand. Can you?
I'll try again.
So yeah. Yeah.
So basically, instead of taking saying, okay, we look at professor and then student topic identify professor, and student and professor identify topic, can we look at each subset? So each like single subset saying, okay, we look at topic and professor, which is a one-on-one relationship. And then we look at the relation topic to student. And if both of these relations are not violated in the instance, then it's okay.
Okay, so intuitively I would say no. Okay, so I don't have the answer right now, but I can tell you the way to check it. So the statement you have can be written as a precise logical sentence, right?
Sure.
And you can see whether that can be proved by essentially this.
Okay.
I don't have I would say no, but I don't have a counter example at this moment. Yeah. So if you send me an email with that sentence, I can give you a counter example, or I can prove it. Yeah.
Okay. I'll write down.
Yeah. Cool. Yeah. So I mean, if you think about like why do we have the formal semantic, it's just it actually gives you a way to answer that type of question. So essentially, otherwise we are going into an endless discussion about this, and we all get confused. This diagram means this too. Okay, that's it. I mean, it's a programming language. This is a semantic, right? And then whatever statement you want to make, if they can be proved by this tool, fine, right? Otherwise, no, right? And otherwise, you get the counterexample, right? Yeah. So like, send me that sentence, and then we can look at it together. Okay. Cool. Great. Okay. So now this is the last example of today. Let's look at what we have here. So here we have student, lecturer, assistant, professor, right? And we have a whole bunch of kind of cardinalities. So let's take this example, gives, right? Professor gives lecture. So there is actually one-to-many relationship between professor and lecturer. This actually means that if I know lecturer, I can uniquely identify a professor. Okay. Sorry. If you take test, this one actually means that if I take student and lecturer, I can identify a professor. Okay. So, and you can do this exercise by yourself. If I know the assistant, I can identify a professor, which means that one assistant like can only work for essentially one professors, right? So like you read this diagram, right? So that actually tells you all those constraints about the relationships. Okay. So here, one thing that you can see, there's sometimes M, sometimes N, right? So it's just like whenever you have this type of things, right? So you want to make sure they are different, right? So sometimes if you write both as N is also fun, right? So like this is not that important. Like whether you write I'm here, or N here, or N here, or I'm here, right? It doesn't really matter. Okay, so yeah, so I think that's all for today. In the on Friday, we are going to talk about essentially a more expressive way to specify cardinality. Okay, and we are going to talk about some advanced kind of things you can actually specify in an ER diagram. And we are going to talk about how to translate an ER diagram, the conceptual model, into a relational model. Okay, so that's all for today. If you have any question, I'll be here to answer them. Otherwise, I will see you guys on Friday. Yeah, thank you. Okay, so we have one question. So Alex, can you speak up? Yeah. Easier if we. Yeah. So like, which slides do you mean?
Yeah, sure. The slide before.
This one.
The big one with
one?
student, lecturer, assistant, and professor. It's slide 46.
This one?
Yes, that one.
Okay, cool.
Their grade is an attribute.
Yes, grade is attribute. So
And-
grade is it's a concrete value, right?
Yeah, and I thought we defined relations on abstract values only.
Oh yeah. Good. Yeah. Yeah. So that's a very good. Yeah. So that's a very good. Yeah. Sure. So like here, like essentially, yeah. So we are missing one definition to say a relationship can also have an attribute. So this
okay.
relationship is still a relationship between three entity sets. That doesn't change. But relationship can also have attribute.
Okay, sure.
Yeah. So like
just
which means
wanted
that
to
for
make sure.
like for every single tuple between student, lecturer, and professor, you associate a grade. Right. So
Yes.
like you can define that similarly, right? So essentially, as long as S, L, and P participate in test, it implies that there exists a grade participate in in that attribute, right? So like you can define that very similarly as the attribute for entity set.
Okay, thanks.
Yeah, cool. Cool. So if there's no other question, I'll see you guys on Friday. Yeah, have fun.